Hi, welcome to module 10 of this course. In this module we are going to learn minimization of corner maps in the presence of what is called don't care conditions. So, at times what happens is you have minterms for which the output is actually a don't care. So, what we mean by that is these input combinations. So, we talked about if you have n inputs you will have 2 power n input combinations, but sometimes some of these input combinations may never occur in the real world. If such a thing happens, what you would want to do is to be able to treat the output, if such a condition has to be treated in the K map, as a don't care. So, the reason why this is useful is that when you minimize in the presence of what are called don't cares, you can actually cut down the complexity of the circuit. You may actually start using lesser number of gates than what you would have otherwise. So, the setup is as follows. So, you have several input combinations, 2 power n input combinations, of which some input combinations never occur, and you would want to treat those minterms in a different way. So, the don't cares or the output for these things are not ones or not zeros. So, they could be treated as ones or zeros because the output does not matter at all, and such things are marked as x's, and when we simplify in the K map, we can either treat them as zeros or we can treat them as ones. So, let us take a small example. So, I am going to give you a number, a 3-bit binary number, and the 3-bit binary number I am telling you that it can take values from 1 to 5. So, if I tell you that there is a 3-bit number, all combinations from 0 to 7 are possible, but in the circuit that I am designing, let us say I am interested only in the numbers 1 to 5, then the number 0, number 6 and number 7 do not appear in the inputs, and I can treat them as don't cares. What I want here is I want to count the number of ones that are there in the input. So, it is a 3-bit input that I am going to give, and of this you have to count the number of ones that are present in the input, and the additional constraint is that we want to use only 2 input logic gates. So, given any design problem like this, the first thing you want to determine is the number of inputs and the number of outputs. So, the numbers are between 1 and 5, we need only 3 bits for that. So, that is 3 inputs, and if there are 3 input bits, I can have at most 3 ones in it. To represent 3, I need 2 bits. So, I will have number of inputs equals 3 and number of outputs being 2. So, we are now done with the basic black box. As a black box, it is going to take 3 inputs and it is going to give 2 outputs. Now, let us go and look at the truth table. So, the truth table is as before except for some few changes. So, let us look at the truth table. I am going to number the input bits as B2, B1 and B0, and the output bits are going to be named Z1 and Z0. So, we have 3 input bits and we have 3 output bits, and for these 3 input bits we have 8 combinations, and of the 8 combinations I already mentioned that this minterm 0, minterm 6 and 7, these inputs are not valid inputs to this circuit. So, what we can do is we can mark their outputs as don't cares. So, Z1 is a don't care if the input combination is 0, Z0 is also a don't care if the input combination is 0. The same thing happens in these two. Now, let us go and look at what happens from rows minterm 1 to minterm 5. So, for minterm 1, if you go and count the number of ones, there is exactly 1 1. So, that is marked as 0 1. So is it for number 2 and number 4. So, number 1, number 2 and number 4 has only 1 1 in them. So, you have those rows with only 1 1. Number 3 and number 5 they have 2 ones in them. So, we have them as 1 0. So, the rest is don't care. Now, you want to go and minimize this. So, let us see how to do minimization of this. So, the first thing is there is nothing magical about these x's. You can do the same thing that you did for taking a truth table and entering them into a K map. So, as before we have B2 which goes along the rows and combinations of B1, B0 that goes along the columns, and notice that it is 0 0 0 1 1 1 1 0, and you take the entries from here and plug them here. So, you have x 1 0 1, that is how you should enter it, x 1 and then a 1 and then come back and fill in a 0, then 1 0. So 1 0 x, come back and fill x. So we have that now. Now let us think about minimization of this. So if I go and minimize this, you notice the ones that we have here are not adjacent to any other ones. So if we want to write this directly, if I treat the x's as zeros, then I would not map this with anything, not group this with anything, not group this with anything. We will have 3 product terms in this. However, the moment we have x's, something interesting happens. So first thing is, if you go and look at these two ones, they both have adjacent x's next to them. So I can group this 4 together, and if you look at this one, it is adjacent to this x, I can group this together. So what I am going to do is I am going to treat this x and this x as a 1. Remember, it is a don't care, I do not really care about the output if some other min-term like 0, 6 or 7 comes through. So I can as well go and treat them as 1s. So if it is a junk input, you get garbage in and garbage out. So in this circuit I am supposed to be taking only 1 to 5. If you feed 0 to this, then the output is not something that you can expect to be correct. So now I can treat these x's as 1s. Let me group them. So when we group them, these 4 this quad, as we call it, this x 1, 1 and x is called a quad. So in the quad we have 4 terms, and the quad minimizes to this term b naught complement. So you can notice that. So b2 is straddling across 2 rows. So we cannot have b2 in the term. If you look at this column and this column, only b naught is remaining steady at its complemented value. So you have b naught complement. And if you go and look at this grouping, again we have used x equals 1, x as 1 here. So this belongs to the row b2 complement, so that is 0 here, and then you have b1 complement coming from these 2 columns. So the overall result is b naught complement plus b2 complement and b1 complement. The interesting thing to notice in this one is this x is not grouped at all. So it is a don't care, and if we want to use it, we can use it as a 1, but if it is not going to help us, we do not have to use it at all. So just taking this term and putting another product term is not necessary, because it is supposed to correspond to min term 7 anyway, and min term 7 is not a valid input. So I can treat this x as 0 and leave it as it is. So what we have done is we had 3 x's, 2 of them we used it as 1s, and one of them we are using it as 0. This is perfectly acceptable because the value of x is really a don't care. We should be able to use any combinations of zeros and ones for the x's that are there. Now let us go and look at Z1. For Z1 the table is as follows. So you have 2 1s, so there are only 2 places where there are 1s, and there are 3 places where there are zeros, so we have them, the rest are x's. Now again, if we had not done any minimization with don't cares, this will be an individual term and this will be an individual term, and you would have 2 product terms, and the 2 product terms would each have 3 literals in them. So this will have a literal which is b2 b1 complement b naught, and this one would have been b2 complement b1 b naught. So each one would have had more literals in them. Now let us see what happens to the grouping. So this setup, this red one, so there are 2 kinds of groupings that are shown here. One grouping that is shown in red is the sum of products, and the one that is shown in green is the product of sums. So let us start with the sum of products. So this x, if I treat it as 1, I group it together, that will cut down 1 term, and again I can do the same thing here. So this term is b2 and b1. So this term, the horizontal one is b2 and b naught, and this one is b1 and b naught. So that is what we have here. So this is b1 b naught, this is b2 b naught. So the sum is given here. So it is sum of products. In the same picture you can also notice that if you have zeros, you can group them together. So I have these 3 blank positions which are zeros, and we have 2 x's in the 2 corners, and this makes a quad of zeros. So if I treat this x as a 0 and this x as a 0, we get a quad of 4 terms, that is a 0, and then this 0 can be grouped with the 0 which is neighboring to it, and this gives us this expression. So this quad is just B naught, because if you notice this is straddling across these two rows, so B2 cannot appear, it is straddling across the first and last column where B naught is steady and it is marked as 0. So it comes in the uncomplemented version, and this one is in the row corresponding to B2, and you get B1 from these two columns here. So it is B2 or B1. So it's actually, you can also verify that these two are the same. So what this picture is showing is that the don't cares can be used as ones or zeros. You usually treat x's as zeros, where if you want to combine them if you want to get product of sums, you will start treating x's as ones and combine them if you want to do sum of products. And in either one you can actually leave out x's if it is not going to help in minimizing anything. So for example, in this one we notice that this x is not adjacent to any 1, there is no point in treating this x as a 1, we instead treat it as a 0. So this is the gate level implementation for this circuit. We have B2, B1, B0 going into this part of the circuit as well as this part of the circuit, and it is a straightforward 2 input implementation of the circuit. So let us look at another example here. In this example we are going to design a circuit that will increment a BCD digit by 1. So BCD stands for binary coded decimal, and I will show you what it is in the piece of paper soon. So binary coded decimal, we are given an input which is binary coded decimal, and we are going to increment it by 1 and produce another output binary coded decimal digit. So let us look at what a BCD is. BCD stands for binary coded decimal. So let us look at this number called 45 here. So 45 in BCD is as follows: you take the number 4 and you write the binary equivalent of it, which is 0 1 0 0, and you take the number 5, you write the binary equivalent of that, which is 0 1 0 1, and if you put them together or concatenate them, you get the sequence 0 1 0 0 0 1 0 1, and that is the binary coded decimal representation of 45. So what you do is you take the decimal digits, and for each digit you put the 4-digit representation for it, and you put it from left to right. That is called BCD. So remember, BCD is not the same as binary representation. If you look at 45, the binary representation of 45 is not this. So 45 represented in binary is given here. So this is 32 plus 8 40, then 44 45. So this is 45 in binary. So if you notice, this 45 base 10, this has positional information. So this starts with 2 power 0, 2 power 1, 2 power 2 and so on, whereas this one is not positional. This, you do not assign weights to each of the bits and add them up. So binary coded decimal is slightly different. So let us switch back to the problem statement. So in the problem statement what we have is, we say that we want a circuit that will increment a BCD digit by 1 and produce an output BCD digit. So let us see how that can be done. So first of all, if you notice, the decimal can only be from 0 to 9, and when we increment, 0 will increment to 1, 1 will increment to 2 and so on, and 9 will increment to 0. So this is what we want. So we have rows from 0 to 15 here. So 0 0 0 0 stands for decimal 0 here, and when we increment we get decimal 1. So when we increment decimal 7 we get decimal 8, when we increment decimal 8 we get 9. However, when we increment decimal 9 we get decimal 0. So imagine this is like a speedometer rolling from 9 to 0, right? That is what we are having here. So in the binary coded decimal, each decimal gets one 4-bit value, right? So number 10, 11, 12 and so on, so this combinations minterm 10 to minterm 15 cannot happen because a single digit cannot be 10. So 10 is actually 2 digits, one followed by a 0. So you cannot have a single digit with 10. So the circuit is asking to take a BCD digit and increment by 1. So in this case it is natural to see that the cases from minterm 10 to minterm 15 are all don't cares. So that is what we have now. So now let us go and put them in tables. I have already done that for you here. So there are 4 bits W, X, Y and Z, and they are put in their respective tables. In all of these I have used AB along the rows and CD along the columns, and the the tables you can see them here. So they are also grouped in place. So let us look at this one for example. This one can be grouped only with x. You cannot go to the third one because remember we have to group in terms of 2 only. So this 1 and x forms one thing. This x1 and xx actually forms a quad. So this is a very interesting example. There is 1 1. If you had left it alone, it would have resulted in something, but then it is in the adjacency of 3 other x's which makes it a quad. So similarly, if you go and look at these 2 1s here, this would have been a group of 2 1s if not for the 2 x's that we have used here. And in this example, you have 2 1s here and 2 1s here, you would have actually made a quad combining these 2. However, because of the x's here and this 1 in the corner, we can group all of this into a group of 8. So this is the power that you get from don't cares. So notice again, we have left out several x's ungrouped. It's just because there is an x, you don't have to cover it. So I want to reiterate that point. So you put an x, and if you want to cover it as a 1, you cover it. If you don't want it, do not. You don't need to cover it as a term. So let us see the power of what we got from BCD. So I have written this down in a piece of paper. So let us look at W. If we had to minimize it without the usage of don't cares, we would have had this term A, B bar, C bar, D bar. This would have been one of the terms, and A bar, B, C, D would have been the another term. These are the 2 terms that would have been there. Both these terms would have been loners in the K map. So to implement this, we would have needed 3 AND gates and 3 inverters. To implement this term, you would have needed 1 inverter and 3 AND gates, and you need 1 OR gate here. So overall you would have needed 6 AND gates, 4 inverter and 1 OR gate. But with don't care condition, the expression that we have is AD complement plus BCD. So in both these terms, some variables, some literals are knocked off. So this requires 1 AND gate here and 2 AND gates here. So that is 3 AND gates, 1 inverter plus 1 OR gate. So the usage of this don't care condition is helped in minimizing the circuit for W quite a bit. So we should keep this in mind. If you don't need the x's, don't use them, but if it can reduce the complexity of the expression that you are putting there, then use it as ones. If you are going to do POS minimizations, then do it the other way around. You treat the x's as zeros and combine them with zeros, but again remember not to combine all the x's if you don't need them at all. So this brings me to the end of the lecture. So I am giving you a bunch of exercises here for as a do it yourself exercises. So try and get the minimum SOP form and the POS form for all of them, and for the ones that are marked with X, see if you can implement them using NAND gates only and NOR gates only. So go and do the exercises for all of them and implement them as SOP and POS, but also implement the ones that are shown with star using only the using just the NAND gates or using just the NOR gates. So go and do this. So this will be an interesting exercise to do, and it will also help you in practicing all the terms that we have learned so far. So this brings me to the end of module 10. I'll see you in a little while in module 11.